Good. So today we're going to look at entity relationship modeling in the first part of the lecture, and then for the second part of the lecture we are going to move on to enhance entity relationship modeling, which just gives you additional semantic constructs to be able to represent the real world. So the first part of the lecture we are talking about what we call entity relationship modeling and entity relationship diagrams, and what we want to do is we'll start by talking generically about database design, and then we will move on to look at how we might design using ER modeling, how we will draw ER diagrams, and so on. The reading for this part of the lecture is chapter 12. Now, that chapter 12 is the ER diagram, but as background reading, you should also do chapter 10 and 11. These are, chapter 10 covers the generic kind of like design process, how to design a database and what is the software life cycle for that. And chapter 11 tells you all about the analysis phase. So how do you analyze the requirements of the user for the database? We're not going to cover that, and I'm not going to examine you on that, but it's part of the database world, and therefore it's a good thing for you to read it and be aware of the kind of things that happen. But we won't cover it in the course. So what we want to do when we're designing databases, and this is, if you read chapter 10, you will get to understand more about this, is we really want to follow a structured approach, much as we do with any kind of designing of software. If you follow a structured approach, you have a better chance of the project working, of it being on time, of it delivering its objectives. And that means that there are serious activities that we do, generally sequentially, but a lot of these type of development life cycles are iterative and interactive. So you go back to, from one stage, you go back to the previous stages, and so on. And generally for a database, the first thing that you're going to do is try to do the database planning, so start thinking about the business needs and what the business requires in terms of the data it needs to store and who might need to access it, etc. And how you are going to deliver these database projects. So a lot of database management, general management activities, so thinking about how you schedule the project, how you allocate resources, etc. So that will be the first part of trying to design a database. The next thing that you might do is systems definition, so looking at the boundaries of the system, the different user views and so on, trying to understand what users are going to use the system. And from there, we will then go on to what we call the requirement collection and analysis, and that's the part that is covered in chapter 11, if you're interested. So how do we actually get to understand what the user's requirements are, how do we formulate them in a way that we can later on in the process come back to make sure we are delivering on those requirements, etc. Now, having done all of that, then we go on to the database design, and that is the part that we're going to talk about today in more detail in the lecture. And then once that is done, we might select what DBMS we are going to use. In our case, it might be a Postgres SQL database management system. So then we have to refine the database design for that particular DBMS, and then we will go to implement the system, test the system, etc. And eventually deploy it in the real world. So when we think about database design, what we are trying to do, like everything, a database should be designed. Most objects that you use have to be designed, because if we don't design the things and we start to implement them before we design them, what we tend to do is make a lot of mistakes along the way, because we haven't thought about all of the requirements, and therefore suddenly we have to kind of make haphazard decisions to provide some requirements that weren't thought of in the beginning. So many databases aren't designed properly, unfortunately, but that leads to very poor then delivery of what the user needs, because they haven't been designed. So it's important, if you get involved with databases, that you are aware of the design process that should have occurred, and if you become a database designer, it is important that you understand how this is done properly. So what we're doing is we will try to create a design for the database that will support the whole entire enterprise, because remember that when we talked about databases, we moved on to a scenario where the data has to be providing a resource for the whole entire enterprise, not for a particular department, but for the whole entire operation of the company. So we have to make sure that we provide the data to support the enterprise in delivering all of its objectives, that we look at the mission statements of the company, and that we're going to be able to deliver a resource that the company can use to meet those objectives. So that is what we are trying to do when we design a database. And there are a number of approaches that we can do that. We are going to look today at what we call the top-down approach. And this is done with ER diagrams. So we're going to look at how we design databases using this type of top-down approach. But there is also a bottom-up approach of designing databases, and that's through the process of normalization. In the next lecture, we will look at how we design databases with normalization. Now, normally, we will advocate that you do not use normalization to design databases. You design them using the top-down approach, the ER diagram, but then you use normalization to check that your design is a good design. Because if your design is normalized, then it is a good design. So generally, we use normalization to check on the output of the top-down design using ER diagrams. There is also a mixed way of doing it. And as I said, you might use the second part, the normalization, to check that your design is a good design. So when we look at database design, what we are trying to do, as we have said before, is to create a data model, a model of the real world in the computer, so that we can express the objects that exist in the real world and the relationship between the objects. And what we want with this data model is we want to be able to do a number of things. One of them is understand the meaning or the semantics of the data, and the other one is to communicate between the different stakeholders in the database development process. So you might have users, database designers, database administrators, and our design is going to help us to communicate unambiguously about the database. So it's going to be a communication tool. So when we think about, have I noticed on that? Oh yes. What we want to do is we want to look at the data model. We want to create a data model that is going to answer all of the questions that we have that have been raised by the requirements. So the main things that we're going to have to do with our data model is identify the entities that are going to be representing the objects in the real world, the relationship between the entities, and the attributes of those entities. This is what our design is going to convey in terms of what appears in that design. So the other thing that we want to have through this design is, remember that our conceptual database is going to support a number of different users' views. So this data model that we generate, this design in the form of the data model, is going to be able to support each user view of the data. So it has to support different user views of the data. And it's also going to help us to understand the nature of the data independently of the physical representation. Remember again that when we talked earlier about databases, we said we wanted to provide this concept of independence that was very important to us, where we can separate how we store the data, the structure of the data, from the access of the data and from the implementations and the physical issues in the data. So again, we're trying to provide, through this design, this idea of independence. We are trying to come up with a data model, but we don't want to be thinking at this stage about implementation constraints. This will come later when we move on to doing the physical design. At this stage, we're talking about the higher level of the design. And we want to make sure that we can provide different user views, as I said. So the design is going to be having three phases in which we work. First of all, we have the conceptual design, and that is the process of constructing a model of the data, which is going to be used in the enterprise, independent of any physical considerations. So we're trying to think about what data do we need without really concerning ourselves with how we're going to store the data, how we're going to access the data. what we want to look at is the conceptual data model. So what data do we need to support the business? And then we are going to use or design or this database looking at the information that we got in the requirements document. So in the analysis phase, which we haven't looked at, we would have come up with a set of requirements for the database. And what we're trying to do with this conceptual model is we're trying to meet those requirements of the database. Once we have done that, then we got to look at what kind of a data model are we going to use. In our case, it's going to be the relational model. So we have to translate this high-level conceptual design into something in the relational data model. So that is going to be a set of tables that are related via the foreign key, primary key links. So we translate our high-level conceptual design into a relational data model design, i.e. a set of tables that show the relationships and the constraints of the data, and so on. Again, when we're doing this, we're still not looking at the physical implementation. So we're not thinking about which DBMS we're going to use, how we're going to implement our access methods, or anything like that. Finally, we do our physical design, and that we will cover in a different lecture, which Dan will do for you. And that is looking at how we are going to implement this design for a target DBMS, and then starting to look at things like access methods, indexes required, etc. So that will be the last stage of designing, where we actually begin to concern ourselves with the implementation of the database model. So at that point, we have to look at what are going to be the base relations, the file organization, and indexes that we are going to use. How efficient is the data access? Is there optimization that needs to be done by building further indexes, etc.? What are the integrity constraints? What are the security constraints of the data? That is decided at the physical design stage. So those three stages correlate to our ANSI Spark architecture like this. If we remember, we're always talking about this in the concept of these concepts in terms of the ANSI Spark architecture, the three-level architecture, because that allows us to always have this idea of independence taken care of. So how does that fit into that? Remember that we have the external schema, which could be a number of them, a number of views, and they were all derived from the conceptual schema, which was the interpretation of the data as the DBA and the operating system sees it and so on, and the user sees it. And then from that we had an internal schema which begins to define the physical aspects of the database, and that then kind of accesses the physical storage. So the first two parts are designed using this logical stroke conceptual database design, and we moved on to the physical database design when we are trying to construct this internal schema and look at the access methods. So that's how things work in terms of the design. Are you all following me so far? Any questions so far? There was something stuck in my eye. I keep walking with something and it's really getting irritating. So what we have is now to look at the conceptual design through this lecture. So we're going to try to understand how we will generate a conceptual design for the database using this ER modeling in the first instance. So we need to think about what kind of information is going to be stored. This will be in the requirements document, because the analysis phase would have actually found out what do we have to store, what kind of queries are going to be asked of the data, who is going to ask those queries, etc. So we would have had all of this information come to us from the analysis process. So remember that at this stage, when we are designing the conceptual model, we don't want to think about implementation issues. We want to remove ourselves from any of the implementation side of what we have to decide later. So we're going to concentrate merely on the data that we have to give, and we are going to try to produce an ER diagram, which is going to give us this view of the data, this conceptual view of the data. Later on, once we have a good ER diagram, we will try to translate that to a particular data model, in our case, the relational data model. And so we will need to transform that ER model into a set of relations that are going to be then implemented in a particular DBMS. So the process is going to be then followed by the physical design. Once we have decided what is our logical design, i.e. we decided the relational model, then we go to the physical design. And at that point, we decide what is our target DBMS, because that might influence some of the implementation details. Then we decide what is the code that we need, the data definition language code, to implement our particular design for a particular target DBMS, like PostgreSQL. And we need to do things like add indexes to make the searches more efficiency. We will be thinking about using the standard SQL, because that is portable from one system to another whenever possible. There might be times where we cannot use the standard, but whenever possible we will stick to the standard SQL definitions, because that makes our code more portable from one type of DBMS to another. Once we've done all of these things, we will implement a database. Initially we'll add some test data, so we'll have to think about a set of test data that is good enough to test most of the conditions the system could find. So for example, wrong conditions as well as right input we have to think about. And once we have tested this design and this first implementation, then we might code some sample queries and see how the system responds to those queries, refine the design if we find there are areas of the design that are not particularly performing well, where we're not getting the right data. And then finally, once we are happy that the design is correct and we have an initial implementation, we will load the operational data, the real data, and then we will release that database so that programmers and end users can ask queries of the system, build applications that ask data of the system, etc. So we will build external views and so on, and we will release that database. So in terms of the ER model that we are going to look at now, the main thing that we have to understand here is what are the entities, what are the attributes, and what are the relationships. Entities are the objects that we want to represent in the real world. In the real world that we're trying to model, there are objects, and we will need to understand what those objects are. And the objects that we're going to model will have attributes that define them. So if I say a student, the attributes that matter for a student might be the name, the last name, the first name, the course is enrolled on, the previous results, the results for the modules is enrolled on, etc. If I think about a member of staff, it might be the contact details, it might be the salary, the position they occupy, how many years they've been employed by the university, their specialty, etc. So every object will have some attributes that identify that object and matter to the enterprise. And then they won't live in isolation, they will have relationships with one another. So that is how the objects kind of interact in the real world, and we want to capture that in our data model. And what we have to do that is we're going to put that into a NIR diagram, and with that we have our database design. Now, there are a number of notations for ER diagrams. The older one, the Chen notation, is quite often not used now, so I'm not going to cover that. The notation that I generally use is the crow's foot notation. Modulator, not Modulator, the one that you use now, which is Visio, supports that. It also supports UML. So it's up to you whether you want to use one or the other. I don't mind, as long as you use one or the other consistently. If you do it through a piece of software, you will have to, because it doesn't allow you to mix. But if you did it in the exam, and you're writing it by hand, you could kind of like go from one notation to the other. Try not to confuse them. They are similar, but stay to one notation or the other. It's up to you. The book follows UML, because UML now is used quite a lot in context of software development. So you could follow UML. I like for the database design the crow's foot notation, because it's more geared for this. But it's up to you, I don't mind, so I will show you examples of both. So when we look at entities, which are the objects that we have to identify, is any object or concept that is identified by the enterprise as having an independent existence. And is equivalent to a class in your programming kind of environment. And when you come to UML, you might wish to model them as classes. And within objects, we have what we call an entity type and an entity occurrence. So a student is an entity type, a generic student, whereas one particular student, let's say John Smith, if there is such a student with a particular student number, is an entity occurrence. So there is a type, which is the generic thing, and there is occurrence, which is one specific object in the domain that we are trying to implement. And some objects might have a physical existence, like a student, an employee, a customer, an order, a part. Other objects might have a conceptual existence, for example, a sale, a meeting, a work experience. They are objects in the real world, but they're not necessarily physical objects that you can touch. In the entity ER modeling, the same as a relational model, we have these concepts of keys, and they coincide with the concept of keys that we have come across before. So we have candidate keys, and we have a primary key that is chosen from the candidate keys, and we have foreign keys. And we can have composite keys. They don't have to be made of one individual attribute. They might be made of more than one attribute. So all of these concepts that you learned when we talked about the relational model still stand when it comes to the ER diagrams. And we have to identify the keys as we go along, particularly the primary key of any entity. So we can differentiate two types of entities when we're talking about what kind of an entity we have. We have strong entities and weak entities. The difference is that strong entities have their own independent existence. They don't refer to other entities for their existence. So they are uniquely identifiable without reference to any other entity. So for example, if I have an employee is going to have its own independent existence in the world that I'm trying to represent. It might have an employee number, a surname, a middle name, a title, an address, and a phone. So that is one entity type, and then there'll be instances of that. That exists without reference to other objects. So from that point of view, it's a strong entity. If on the other hand, I want to look at a weak entity, what happens is they exist with reference to another object. So if, for example, I talk about something like the work experience of an employee, that only exists in the context of an employee. So that is what we call a weak entity. If I call about the dependence of a student or a member of a staff, they exist in relation to the other entity. So that is what we will call a weak entity type. So work experience is going to exist in relation to an employee, and it might be composed of the employee number, the job title, and the start date, and then there might be an end date as well. So it is something that exists in the real world, but it exists in relation to another entity type, i.e. to an employee. Are we all happy with that? Now, having understood what an entity is, the next things that we need to understand is how do we define a particular entity. And this is by defining the attributes that make that particular entity. So an attribute is going to be any property of an entity, and relationships could also have attributes in some cases, as we will see later. So they are a property of an entity, but possibly also a property of a relationship. So kind of examples that we might think of: the student name, the age, the date of birth, the languages spoken, the sports that the student plays, anything like that, the hair color, an invoice value. All of those might be properties of a particular object. So they are attributes. Now, for every attribute, again, in coincidence with the relational model, we got this idea of the domain, the values that are allowed for a particular attribute. And my domain might be an easy to define domain or a non-definable infinite domain. So I can have a domain such as sex, which is very easy to define because it's only either male or female. I can have a domain such as age, which is also easy to define for a person because it's going to be 0 to 120. Or I could have much harder to define domains, such as address, etc., where all I can define possibly is the data type, i.e. is going to be a test string. So I might not be able to define that domain other than by the data type. So the data types and the constraints that we can put on the data are what defines in a DBMS the domain. So we're going to define domains later when we go to implement this by saying this, for example, age is of integer type, and I am going to set a constraint that it has to be between the value 0 and the value 130. I might only be able to identify the data type if my domain is difficult to define, like address. Okay? Are we all happy with that? So there are a number of different types of attributes that we might have. We can have simple attributes, which are composed of a single component, so only one component in the attribute. And they are also referred to as atomic attributes, so age. We can only have one value of age, so that's a simple attribute. Salary, we can only have one value of salary, so that is a simple attribute. Or we can have composite attributes, which have multiple components, each of them with their independent existence. So if I have the student name as a whole, that should be a composite attribute because I have the title, the first name, the initial, the middle name, and the last name. So I could see it as a set of simple components, or I could see it at the higher level as a composite attribute. Again, if I talk about the address, I could just say the address, and I see it as a simple attribute, or it in fact is made out of components, so it's a composite attribute, because I have the number of the house, or the name of the house, the street, the village, or wherever, the county, the postcode, and the country. So it is made of components, so that's what we call a composite attribute. We also can have derived attributes, and those are attributes for which we do not store the value, but we derive the value as we need it. So for example, age, I am not going to store, because I'll have to be updating the database constantly to keep the age field current. So what I store is the date of birth, and then I derive the age for a particular student by using today's date. So that is what I call a derived attribute. We can have single valued attributes, i.e. those that can only take one particular value. So for example, age takes one value, height takes one value, weight takes one value. Or I could have multi-valued attributes. And these are going to be things like languages spoken. I speak Spanish and English. Some of you might speak French, English, German. So you can have more than one value for that. That doesn't mean that we can store it in the database like that, but here we're looking about the conceptual model. So at the conceptual level, there can be attributes that have more than one value. The same for sports played. I could be very sporty and playing 5 different sports, and so on. And then we have this concept of key attributes that we talked about in the relational model context, candidate keys, and foreign keys, and primary keys, which are just attributes that are designated because they uniquely identify an object in the model. So if I look at the UML diagrammatic representation in an ER model, and this is the kind of thing that you're going to find in the book, because this example is for your book, what you're going to have is, this is not part of the ER diagram, this is just there to illustrate to you what each part means. So these circles with the arrows are not part of the ER model, they're just there to tell you now what everything is. So what is part of the ER model is the rectangles, which represent entities, and they have the entity name on top, and then the list of attributes inside. So there we have two particular entities, the staff entity and the branch entity. And each of them has a primary key, which is defined by this pk in the UML notation, and then they have a set of attributes. Now, in UML, you might be able to do something like that, where a composite attribute is then annotated with the different composition attributes that form part of that. So here we have a composite attribute. You might not be able to do this in the other notation, in the crowsfoot notation. And here we might have a multi-valued attribute, which is designated by saying this might have 1 through 3 values, because we can have a home number, a work number, and perhaps a mobile number, and so on. And if we have something like a derived attribute, we might put a slash in front of it to indicate that this is a derived attribute. It's not something that we store. We derive that value from another value in the database when we need it. So that is the total count of staff. We're not going to store that, but we can generate that as we need it. And this is what gives you the relationships, those lines give you the relationships in the UML notation. And the arrow tells you how you read that relationship. So you read branch has a staff, and you read staff manages branch. So the arrow tells you which direction you read that relationship. Are we all happy with that? Clear? Crystal clear. Fabulous. So you could use this if you want. Or you could use this, which is what we call the crowsfoot notation. The crowsfoot notation is called like that because the relationship has this kind of three, whatever you call it. It looks like a crowsfoot. And that's why it's called crowsfoot notation. So in that notation, it's very similar. We have the entities still identified by a rectangle. The name of the entity is on top as it was before. The primary key is highlighted with the word primary key. Foreign keys may be highlighted like this with the word foreign key. And we have a set of attributes. We could use the slash in this particular notation if we want to denote that an attribute is a derived attribute. It might not be so easy here to derive a composite attribute because it doesn't kind of like allow you to decide. So you cannot define composite attributes as you did before in the other notation. But you could potentially enter something like this at this level to say the telephone number is has more than one value. It's a multi-valued attribute. Okay? And the relationships are going to be represented by lines, and they are going to have, if they are one to many, they will have, this is a one end, so this is one staff member manages a branch. This is a one to many. We will see the cardinality issues in a minute, so don't worry about that. But that is what defines the notation, is the crowsfoot in the relationship. So it's very similar from that point of view. So are we all happy with that?
Beatrice, can I just ask again about the composite attributes in the crowsfoot?
Yes. You can't really, you don't have any way, as far as I can see in Visio, of defining a composite attribute. So you're going to have to put the individual components as attributes. You cannot establish that this is a composite attribute. That might be so in UML. I don't know with Visio whether that allows you to do that, because Visio has a UML notation, but it might not necessarily give you as much as the book. I don't know what the book uses in terms of what software they use to derive the... I haven't seen in Visio, which is the software that is available to you, any way to separate a composite attribute into the individual attributes. But it doesn't matter. At the end of the day, you're not going to probably store them as such. So you can either say you have an attribute called address, so then you are going to represent it as a string, and you're going to put everything together, or you break it down into the components and say I have a house number, a street, and so on, and you represent it like that. Okay. By the way, you're not forced to use Visio. If you find some other form of software that you can use that allows you to do UML diagrams, then that's fine by me, as long as the diagrams that you produce are reasonable. I don't really mind which software you use, but in the university what they offer is Visio, which is okay. It's not great. It can be a bit buggy at times, but it does the job. Okay. So that's what you will be using, but you could use something else if you want to, if you have something else available to you. No problem to me. Are we all happy with that? So, because you're happy, you are going to have the answer to this, because you got it all right now. So if we have a UEA student record database, which of the following is going to be an entity? So is a degree program an entity? A degree program like computing science, information systems, systems engineering, whatever. Is that going to be an entity in the database? Yay, nay, yes. Because? It exists. We have a number of attributes that we can keep about it. So who is the program director? What is the profile of it? How many years does it last? And so on. So it's an object in the real world with data in the real world. There is a number of occurrences of that object in the real world because we have different degrees. So we need to store it in the database. So it is going to become an entity. What about a module such as CMPS to B08? Is that going to be an entity? Yes, because? Yeah, we have a module organizer, we have coursework, number of courseworks, we have the lectures that might be part of that, the number of lectures, the number of seminars, the number of labs, the timetable schedule for that particular module. So again, it's a real-world object. There are going to be many different instances of that in the database, because we have 2B08 and MB11 and blah, blah, blah. And we can represent it with different attributes. What about the University of East Anglia? Is that an entity?
No,
No, because
it's only one.
Because it's only one. We already have one instance of that in the university database. There's only one instance, so we don't really need to represent it. There might be some things that we know, like the address, who is the vice chancellor, but at the level of the University of East Anglia, we don't need to represent it. If we were a UCAS database, then we will need to represent it, because then in the context of UCAS, each university is going to have a different kind of like life. But in UEA, there is only one UEA, so we don't need to represent it. Are we all happy? What about Mr. Andrew David Johnson, who is a student? Is he an entity?
It's an instance of an entity.
Yes, it's an occurrence of an instance of a particular entity. So we are going to store him as an occurrence of a particular entity, which will be the student. What about a coursework exercise? Yes?
Yes, of course, yes.
Because?
Because there can be different.
Yes.
exercises.
I can have the number one for this is 10%, the second part is 40%, and I want to store the marks associated with it for particular students. So there's going to be something like who set it, when it was set, when it is due, the percentage of marks that are allocated to it. So there's enough information, and there's going to be enough of them in the system to have an entity. What about the 4th of October of 2012 being the date of registration of a student, for example? No, that is a particular value for an attribute, which may be, let's say, the student registration or the date something is due. So that's not going to be an entity. Okay, if we look at attributes, is height simple or composite? Simple, because it's only got one value. You can only have one height, unless that was like a historical view of a child, not in our university. If the height matters, there will only be one that we store. What about derived? Is it derived from something? No, we just store it. What about a single or multi-valued?
Single.
Single. You can only again have one value. What about the address of a student? Is that simple, composite? Composite, because you have a number of things. Is it derived? No. Is it single or multi-valued? Multi-valued, probably, because we have a student time address, and we have another address for your academic address. So we tend to have two in this system, at least. What about the age? Is it simple or composite?
Simple.
And derived? Yes. Is it single or multi-valued?
Single.
Single. You can only be one age. You might like to be a younger age, but still one age. What about the sports play? Is that simple or composite? Composite? Simple, because it's only going to be made up of one component. But is it single or multi-valued? Multi-valued. So it's different single to multi-valued. Single means how many components there are. Multi-valued means can we have more than one value of the same. Okay. What about the year of study? Is it simple? Composite? Is it derived? Yeah, because you could have, what you'll probably have is the year of registration, and then you'll count whether you are in the year 1 of the study, year 2, year 3, year 4. So it's going to be derived. Is it going to be single or multi-valued? Single, because you're only going to have 1 year of the study at a time. Okay, so that is all on attributes. What about relationships? Now, relationships and relations are different things. Remember that relations in the relational data model are the tables. Relationships are the relationships, are the how the tables relate to one another. So it's not the same as a relation. The relation is the table, the relationship is the link between the tables. Generally speaking, if we were to analyze a piece of text looking for the relationships, what we look for is a verb or a short phrase. So, for example, if I have something like customer places order, the verb is places. So that identifies a relationship for me between the customer. Now, names tend to be either an attribute or an entity. So names, so when you're trying to find out to do an ER diagram, you read the test, you look at the names, and you look at the verbs. The names, you start to think, must be probably entities or attributes. The verbs are probably relationships in the system, okay? So example, customer places an order, places is the relationship, customer and order are your entities that are related by that. And again, we can have a relationship type, which is the generic thing, and a relationship occurrence, which is the specific real-world object. So if I say IBM, customer IBM places an order for number 3456, that is an occurrence of the entity type places. It's a real-world occurrence or instance of that relationship taking place in the real world. Now, as we look at the notation, in the UML, it tells you which way to read them. In Crowsfoot notation, it doesn't tell you which way to read them, but they don't normally make sense in one side. So customer places order, order places customer doesn't make sense. So you normally know, if you change then you have to go to passive, so you have to say order is placed by a customer. You change to passive voice, then you're okay. So if we look at how UML represents that, again there that circle is not the UML notation, it's just telling you what the diagram is showing you. We will have one entity, another entity, and the relationship, which at the moment here is shown without cardinality or optionality, is just a line linking the two, and the name of that relationship, and how you read it. So that tells me that a branch has a staff. It doesn't tell me how many at the moment, because we haven't gone into cardinality. So that arrow tells me the duration of the relationship. Now you can have binary relationships like that, like the one that we saw before, or you could have ternary or quaternary relationships. So relationships don't always just involve two entities, they might involve more than two entities. So for example, I could have a quaternary relationship here where I have a solicitor and a buyer and a bid and a financial institution. They're all related together in one relationship because I have that a solicitor arranges a bid on behalf of a buyer supported by a financial institution. So that's a complex relationship. The four objects intervene in that one relationship. UML allows you to do this because what you have when you have a complex relationship is you have this diamond notation connecting the different entities. Crowsfoot notation does not have that. So you're going to have to break it down if you want to represent a complex relationship in Crowsfoot into the different relationships that make that. Okay, so you don't have that kind of notation in the Crowsfoot. So the next thing, oh, that came out after. I thought there was something missing. The relationship, so that's the binary relationship there. That is the quaternary relationship at the bottom. So, oh, there's even another one. See, because I have got these slides out of the book slides. They have actions that I didn't realize attached to them. So they are deciding to pop in as they want. I thought there's things missing in this slide. Now they turn up. So this is our ternary relationship where I have a staff, a client, and a branch. And it's a staff register client at a branch. So that is, in essence, a ternary relationship because there are three things that are interacting together. And again, we define them by a diagram. The other thing that we might have is recursive relationships. And that is where an entity is related to itself. So in that case, I have a recursive relationship. And I can have roles, as we will see in a minute, shown on the diagram for when a particular relationship occurs. So this will be the Crowsfoot notation to show a recursive relationship where I have the entity employee, which supervises a number of employees. So that is an entity which is interacting with itself, having a relationship with itself. I can also represent that in UML, and I just have the staff supervises a staff, okay? And I can have roles. I could have roles, so I could say this is as a supervisee, and this is as a supervisor. So it's a staff appearing in that relationship in different roles. At the end of the day, they both are representation of the same thing. Are you all happy with that? Yes? Static? Very happy? Good. Fabulous. So, as I said, you can have not just two things associated by one type of relationship, but you can also have more than two relationships for two particular entities. So, for example, I can have an employee manages a branch, an employee works at the branch. So those are two different relationships which might give me different roles for those two entities. So I have that the employee manages 01 branch, and the branch is managed by an employee, and at the same time the branch has many employees, or an employee works at a branch. Many employees work at a particular branch. So I have two different relationships connecting two entities. So I can have more than one relationship between two entities because there are different roles there. Okay? Are we happy with that as well? Okay. If I wanted to do that in UML, again, I have a notation for that. So I might have a branch and a staff, the manager's relation, the has relation, and so on. So, and I can give them role names if I want to in UML. Now we move on to the part of the structural constraints, which is where we look at the cardinality and the optionality of the relationships. And this is going to be, first of all, we look at the cardinality. And this is going to tell you the number of possible relationships for each participating entity. So if I have a one-to-one relationship, it means I have one entity occurrence on one side and one entity occurrence at the other. So for example, if I say a school has a dean or a head of a school, and the head of a school is only head of a school to one school. So that is a one-to-one. Each school has only got one dean. Each dean works only for one school. So that is a one-to-one relationship. At the end of each side of the relationship, there is only one participating object. Okay? And in UML, we're going to represent that, in Crossfoot notation, we're going to represent that as a line with a little sort of like line which represents a 1. So that is one-to-one. In Crossfoot notation, if I want to do one-to-many, then this will be the one end and this will be the many end. And that means that I have one participating object in one side relating to many on the other side. So for example, a customer is going to place many orders. Each order relates to only one customer. So that is a one-to-many. The customer places many orders, but the order is associated with only one customer. So that is a one-to-many relationship. Those are the ones that we mostly have in the real world and that we can easily process in the database system. We can also have many-to-many. If we have many-to-many, as we will see that later, we cannot model them in the relational model. We're going to have to break them down into one-to-manys. So something that is many-to-many is a student and a module or a unit. Many students take the same module. Each student takes many modules. So that is a many-to-many. So each of you take more than one module, so you have many modules enrolled on many modules. Each module has many students. So the relationship between a student and module is many-to-many. I won't be able to represent that in the relational model. I'm going to have to break that down. And we will see how we do that. So, as well as the cardinality, the other thing that we need to worry about is the participation constraint. And that determines whether the existence of an entity depends on it being related to another entity through the relationship. So if I have a mandatory relationship, to express that it is mandatory, I will say on the many end, that will be mandatory at the many end or mandatory at the one end. And what I want to say by that is that, for example, if I have a customer and an order, here I'm saying the customer end is mandatory, the order end is optional. So what I mean by that is that the customer can exist in the system with 0, 1, or many orders. So I can have a customer without having any orders associated with him. Or I could have one order, or I could have a number of orders. Okay? On the other hand, each order must have at least one and at most one customer associated with it. So it is mandatory. An order must always be associated with a customer, but a customer may not be associated with an order. Okay? So we express this by saying this is mandatory at the one end because I got this mandatory thing. This is optional at the other end because I have the optionality here. Equally, a student and a unit. I have made them many-to-many optional at both ends. And that means that I could have students in my system that are associated with no units, 1 unit, 2 units, or a number of units. Equally, I can have units in my system that have no students registered, 1 student registered, 2 student registers. Do we get this? Now, we need to look at the real world to decide what is correct. So should I be able to have in my system? And generally, you do this by making assumptions. So for example, if I'm going to design a database for the university, and I look at this, and I think, is there a reason to have a module that doesn't have any students allocated to it? Could that be in a university that we have a module with no students?
Yeah.
Yes, because maybe, nobody liked it, but it is an offer. So we should be able to enter it in the system, okay, without having any students associated to it. So then we're going to make that optional. And we're going to say, we are assuming that we could have modules for which no student has enrolled, or it's a new module and it has no enrollment yet, or anything like that. Could we have a student that has no modules for which he is enrolled?
Yeah.
Perhaps, if he's intercalating, maybe, he's taking a year out, he's not enrolled on anything, so maybe I could say it is optional then. If in the real world it's not ever going to be optional, then I should make it mandatory, okay? Because then that depends on whether that object is going to be allowed in the database with or without. But for a customer, it is quite clear that we might want to, do we want to register a customer that doesn't have any orders? Yeah, because sometimes maybe a customer comes, let's say it's a website, they look at it, we get the details, they don't make any orders, but we still want to capture them, to have them there, because if we have a promotion, we send them details. Do we want to have an order that is associated with no customer? No, because then what do we know about this order? So we cannot have that. So in that case, we have to make it mandatory. Okay? So do we understand cardinality and optionality? So when we go to UML, the notation changes slightly. Now UML is more precise in terms of cardinality of an optionality because this is expressed with numbers. So this is a one-to-one relationship. It is optional at this end because I'm saying a staff manages 0 to 1 branches. So that is optional. So we could manage no branch or we could manage 1 branch. On the other hand, I'm saying a branch has 1-to-1 managers. So a branch must have a manager, but a staff does not have to manage any branches. So it's optional at the branch end, mandatory at the staff end, and that is a 1-to-1 relationship in UML. Or if I want to have a many-to-many, then I have something like that. I have a staff oversees property for rent, so a staff can oversee 0 to many properties or rent. So he might be allocated to no properties, 1 property, 2 properties, or many properties. On the other hand, a property for rent is allocated to no staff or 1 staff. So this is 1 to many and is optional at both ends. So I could have properties for rent without the staff allocated to them, and I could have a staff without properties for rent allocated to them. So, and if we have many to many, we will have something like that. A newspaper advertises properties for rent, and we will have that 0 to many, so that is many to many. Newspapers advertise 1 to many properties for rent. Okay? So I have a newspaper can have at least 1 advert, but it could have many adverts. Each advert could appear in no newspaper, but it could appear in many newspapers. So that is a many to many. but it's optional at this end and mandatory at this end. Are we all happy with that in UML as well? Yes? Good. So this is a slightly bigger diagram for you. We have a job type, so there we have a number of entities. A job type, a department, an employee, and a course. And we have them connected, and this is the UML diagram, by different relationships. Each of them has a primary key, and then it has some additional attributes. So I'm here saying here, an employee takes many courses, possibly no course. So this is optional at this end, but it is many to many. A course may be taken by no employees or a number of employees. So it's many to many, optional at both ends. On the other hand, I said a department employs a number of employees, and that is one to many and mandatory at both ends. So an employee must have at least, a department must have at least one employee. Each employee must belong to at least one department. And a job type, an employee includes a job type, and I have that a job type might be associated with many employees. Each employee is associated with one job type. Okay? And this is optional at this end, mandatory at that end. Are we all happy with that? And remember that I said you cannot have many to many. If we have many to many relationships, we have a problem because we cannot translate them to the relational model. So every time we find a many to many relationship, your job is not done. You have to break that down into one to many. So how we do that? We find an intersecting entity, which is going to take the primary key of this and the primary key of this. Okay? So here we have a many to many. An employee takes many courses. Each course is taken by many employees. So that diagram is not finished because we have to deal with that. So if we go back to the crow's foot notation, you get used to both. How we're going to deal with that is we're going to find an intersecting entity. So we say, okay, we have our employee, and we have our course, and what we find is the intersection entity, which might be called course registration, and that is going to tell me an employee number and a course code. And that is going to be many, one to many, because I have an employee has many course registrations. Each course registration is for one employee. A course has many course registrations, but each course registration is for one course. So I have solved my problem because now I have only one to many relationships. So I have an intersecting entity that tells me what employee is registered on one course. I might have additional attributes here or not, but I've broken down my many to many by using an intersecting entity. Are we all happy with that? The process is always the same. We have to find an intersecting entity. So if we look at the previous diagram in crow's foot notation, it might be something like that, where we have a job type, an employee, course registration, and this is where we already broken the many to many, because the ER diagram in Visio, the crow's foot notation will not allow you to have the many to manys. So you'll have to break them down when you want to model something. Okay, so you'll have to find the intersecting entity before you're allowed to put them in your diagram. So we need to break down this so we have our employee and our course, and the breakdown entity is the course registration, our department, and our job type in the crow's foot notation. So we need to resolve in Visio those many to manys before we can actually do our diagram. Okay? And then we also name, although we don't know which way to read them, it tends to be straightforward. Are we all happy with that as well?
What's the dotted line?
Sorry?
Dotted line.
There are two types of relationships there, what they call identifying and non-identifying relationships in Visio. And you will come across this in the labs. So if you define something as identifying, like this, it automatically puts the primary key of the, so when you want to do like an intersection like this, you will use this type of identifying relationship, which puts the primary key at of the other entity in the intersecting entity. And if you define them in the other way, the non-identifying, then you don't have that. So most of the time you'll be doing this, But when you are doing an intersection entity, you will use the identifying relationships, and they will automatically put your primary key in the intersecting entity. But you will come across that in the lab. It's just the way the Visio works. Okay, so remember I said you could also have attributes for a relationship? So for example, if I have a student takes unit or module, an attribute of that might be the year in which the student takes the module. Now if I have attributes in the relationship, what happens is they end up being modeled either in one entity, in the other, or if it is a many-to-many, in the intersecting entity. So they don't stay in the relationship, they end up being part of one of the entities. But initially, in our model, we could come across something like that. So if we did, then what we will do is we will say, okay, the year is an attribute of the relationship, it becomes an attribute of the intersecting entity. The year in which the employee takes the course. Okay, so it ends up being identified with that. If it was a one-to-many, it might end up being identified with the many end of the relationship instead. It's not very usual to have attributes in relationships, but you could have some. And if you do, they will end up being moduled in one of the entities or in an intersecting entity. So equally in UML, you could have them as well, and they will end up being something like this. So these are attributes of the relationship, and again, eventually they will filter into one or the other entities or an intersecting entity. So let's just quickly do that. Oh, today I have a clean board, because I forgot to bring the cleaning thing. So if I have something like that, it says the county library service operates a number of libraries. Each library stocks many copies of a number of books. A citizen might register with one library and borrow many books. So what do I need to do in terms of entities there? Book. So a book might be an entity. And what else? A library might be an entity. Okay. A citizen might be an entity. Anything else?
Borrowers.
Sorry?
Borrowers.
Well, is that an entity? What is it? It's a relationship. Because borrows is a verb. So the fact that it's a verb will give you that is a relationship. Is there any more entities before we look onto the relationship? So we have books. County library services operate a number of libraries. Each library stocks many copies of a number of books. A citizen might register with one library and might borrow many books. Let's think about the kind of like the things that we might have. For a book, what might be a primary key? ISBN. That might be the primary key, perhaps. Title. Also. Genre. Publisher. And so on. Okay, what about a citizen? Title, age, which probably will be derived, surname, name. Yeah, we need to have some primary key, so we're probably going to give them a member number and whatever other things we might have for them. And a library, branch number, location, and the branch number is going to be presumably the primary key, and that's going to be the primary key. Okay, and then we might have some other things. So if we try to identify from there the relationships, we have a library and a book. Is there a relationship there? Yes, because it says each library stocks. So stocks is a verb. It gives you the idea that the library and the book have some kind of like relationship there. Now, is it one to many, one to one, many to many? One library stocks many books. Each book is stocked by many libraries, because if you know, you could have, as we have made a book there, the same book could appear in a number of libraries. So we're going to have many to many there at the moment, because the same book, just because you have a Killing a Mockingbird in this library doesn't mean another library cannot have it. So we're going to have a many to many. So how are we going to break that? Yeah, in fact, it says the country operates a number of libraries. Each library stocks many copies of a book. So, in effect, it's like a book copy that we're talking about, because, you know, we have a generic book title, and then we have copies of that book. So, in effect, we perhaps missed that one entity, but if not, we'll soon know that we need it, because we need to break that many to many, which is a book copy. And if we have a book copy, which is going to have what? Yeah, it's going to have some, it's probably going to have some ISBN number, which is going to be prior to the primary key, but it's also going to be stored in a specific library. It might have a library number within the library. So let's say that it has a branch number. I mean, ideally, that might be also part of the primary key. They would have given that copy a particular identifier within the library, and they will know where it is stored on the shelf. So it will be shelf XD something something in this library. So there's going to be also probably a location within the library where that particular, and there might be more than one copies of one particular book. So there might be unique, there might be 3 copies of the same book, which might all be identified independently or not. But if we have that, then a book, what is the relationship between a book and a copy? Is it one to many? So what is the many end?
Many copies.
Yeah, so a book can have many book copies. Each book copy belongs to one book. Can we have a book that has no copies?
Yes. Unlikely.
Yeah, maybe none of them is out of print, or I don't know, it was something. So possibly a book might have no copies or a number of copies, but we will say an assumption about that. What about a book copy that does not belong to any book? No, so this must be mandatory, okay? What on the other hand about a library and a book copy? Can we have a library that has, what is it going to be? Is it going to be one to one or many to many? Or one to many? One to many, book copy is the many end, okay? Can we have a library that has no book copies for a particular book? Yeah, maybe they didn't like this genre. What about a book copy that doesn't belong to any library? No, they must all be associated with some library. Okay, so that is compulsory. So a library stores book copies. Okay, so what about the library and a citizen? Is it one to one, one to many, many to many?
One library, many citizens.
One library has many citizens enrolled or registered. Okay? Can it have no citizens? Perhaps. You will have to make an assumption about that. Maybe it's new and, you know, it's not. Can a citizen be registered for no library? So this should be optional. So we can have citizens that don't appear in any library, but at most they are registered with what? One library or many? Could be many, although in there says a citizen might register with one library. So it's telling you it's only one, but in a different scenario it could be many. In this scenario it appears to be one only. So then it's one to many. What about a book and a citizen? Do they have any relationship? What about a book copy and a citizen? Yes, because what happens between book copy and citizens?
Citizen can take the book.
Yeah, it says, in fact, it says, a citizen must borrow many books. So if they borrow a book, they don't actually borrow the book, they borrow the book copy. So the relationship is between the book and the book copy. So we have a citizen borrows many book sorry, a book copy is borrowed by many citizens? No?
Not at one time.
But over time?
Yes.
Are we going to store one time or over time? This is a library.
Probably one
What,
time.
do we not want to know what happens to the book over time, perhaps?
I don't know.
Or are we just concerned with the one occurrence of the book?
I think one occurrence.
If we are only concerned with the occurrence, then we have that the book copy is borrowed by only one citizen, but each citizen can borrow many book copies, okay? But if we are wanting to store the history of the book copy through the library, how many times it's loaned and for what period, then we need to have a many-to-many, and we need an intersecting entity, which might be a borrowed record, a loan record, which is for a particular copy and a particular citizen.
On the same token, would you not need one for library and citizen? If the citizen moves, they'll probably want a different library. If you're talking about over history.
Well, it depends on whether the library again wants to keep historical records, but generally speaking, they might only care about the one. But with the copies, you might want to see whether a book is particularly going out and loan a lot or not, you know, so you might want to store the historical information. You've got to think about the scenario and think what you want to model. But let's say that is only one, then we're okay. Can a citizen borrow no books?
Yes.
Yeah.
So that should be optional. Can a book copy be not on loan to anybody?
Yeah.
Yeah, so then that will be optional. In fact, I think the problem there is that as it is, we haven't got anywhere to start the loan period. So when you think about it, we do need an intersecting entity because we have here a citizen borrows many book copies, but somewhere we want to store when is the book out on loan. So I think we need the concept of a loan there because we got to send when is the beginning of and when is the book due. So in fact, we're probably going to need a loan of a book, which is going to be connecting these two, and we're going to have a book copy goes on loan many times, okay, and a citizen has many loans. But each loan relates to one citizen, each loan relates to one book copy. Then we will have there the citizen, or the member number as we called it, which is part of the primary key. We will have the ISBN plus branch number, which is the other part of the primary key for the book copy. And then there we might have a start date and then end date. And that way we can keep track of the loans. Okay?
Isn't the citizen a foreign key? On that?
Sorry?
On the loan, there you've got citizen as a primary key. Is it not a foreign key to this?
Both. It is part of the primary key and it also becomes a foreign key. I haven't identified the foreign keys, but yes, it becomes the link. So it's a primary key but also a foreign key. So these three things are going to be the primary key. This is going to be a foreign key to this, and this is going to be a foreign key to that. So that's how you link them. Okay? We're a bit light, so let's have a mini, tiny, weeny little break.